Okay, in this video we're going to be doing Calc BC Problem Set number 31. The problems and a playlist are in the description below. Let's take a look. Number 1, given dy dt is 1/2 y times the quantity 8 minus y over 2. So notice that there's no t in there. This is kind of implicitly defined. Also, this is a special type of differential equation. This is the logistic differential equation. So you got to know everything about it. It's a very finite amount of stuff to know, but these questions will cover a lot of it. What is the limit as t approaches infinity of y of t? So the first thing that I notice about this is that there's an 8 here instead of the 1 that we need there if everything that we have memorized is going to apply. So I'm going to rewrite this thing. So I'm going to have dy dt is, I need to factor 8 out of everything that's inside the parentheses. So factoring out is equivalent to dividing, but in particular I'm factoring out. So I'll have 8 times 1/2, which is going to be 4, then that y that's sitting there. Now we factored it out, so the 8 divided by 8 is 1 minus y over 2 divided by 8 is y over 16. So now we have the differential equation the way that we want it. We just have to look at it. 16 is definitely going to be the limit. So once you've written it the way you want it, the thing that is underneath y inside the parentheses is the limit. So our limit is going to be 16. Let's take a look at the next part. For what value of y is y increasing most rapidly? So this is another one of those facts that you should know. We've rewritten our differential equation. Y is always increasing most rapidly, or the curve, the solution curve, has a point of inflection at the limit divided by 2. So since that's the case, and we said the limit was 16, we're going to say y is increasing most rapidly for y is equal to 8. Let's take a look at the next one. The logistic differential equation problems, there's just like not a lot going on. All right, part C. If y of 0 equals 20, what is the range of y of t? Okay, so here's our differential equation rewritten. If these were all separate problems, I would have rewritten it every single time. So we know that the limit is 16. Crucially, 20 is more than 16. So what's going to happen is we're going to start at 20 and we'll just decrease toward that limit. Okay, so having established all of that, we can say that the range is going to be between 16, which you will never get to, and 20, which you start out at. And for this one, I thought it'd be useful to just see a picture of this thing. So here's what it looks like. You start above, you decrease until you never actually get there. The graph always looks like it does. All right, let's take a look at the next question. So this is a calculator question. I'm just going to show screenshots. I've done a lot of videos at this point where you can go back and watch me actually do the problems or problems very similar. I'll try to remember to link to those below. Let's take a look. The velocity vector of a particle moving the xy plane is shown above. At t equals 0, the particle is at the point 3, -5. We want to find the particle's position at t equals 2. First thing I'm going to do, even though it's kind of implicitly given to you, I'm going to define x prime and y prime so that I can just use them in my work. So I'm going to say let x prime be 5 cosine t over t plus 1. Let y prime be e to the negative t cosine t. Having established that, what I'm going to do is I'm going to use the fundamental theorem in my favorite way to do it. It's rewriting this as an accumulation function. So I'm going to say that my position at 2, which is x of 2, it's going to be equal to x of 0, where we're starting, plus the displacement. So plus the integral from 0 to 2 of x prime of t dt. I'm also going to write down what y of 2 is going to be, and then I'm just going to flash up a screenshot of what I did on the calculator. So y of 2, it's the same basic idea. It's going to be where you started, which is y of 0, plus the integral from 0 to 2 of y prime of t dt. So you're going to end up doing this a lot with parametrics. So here's a screenshot of what I did on the calculator. Again, there are lots of videos where I go through it step by step. It just takes a lot of time to make those videos. So these are the answers that we got. Approximately 6.209, approximately -4.410, and then I like to write up my answer at the end just so that I've fully answered the question. The position at t equals 2 is 6.209, -4.410. All right, let's take a look at part B of this thing. Find the smaller angle formed between the line tangent to the path at t equals 2 and the x-axis. So if you just think about it, when a line intersects the x-axis, you get like two angles. One of them is acute and one of them is obtuse. We're going to try to find the acute angle, which would mean that we need to end up doing like inverse tangent of a positive thing. So in case you don't remember this, because this doesn't come up all that often, here's a line. I mean, lines come up a lot. Here's slope. So we're like back in algebra 1, right? This is delta x, this is delta y. So the slope is delta y over delta x. There's an angle formed in this right triangle, right? And for that angle, tangent is delta y over delta x, which means that to find the angle itself, we'll just do the inverse tangent of the slope. Since we're in calculus, we think of slope as being the derivative. It's dy dx. So really this question is just saying, what is the inverse tangent of dy dx at t equals 2? The only thing that could cause this to be an issue is if the inverse tangent, if the slope, if dy dx gives you a negative. We have a negative slope here. We'd want to do the inverse tangent of the absolute value. You could like save yourself the problem and always just put absolute value around that, assuming you want the acute angle. I'm not going to worry about it because it's going to turn out to be positive. But that's something to think about. All right, so we need to find dy dx when t is equal to 2, which means we need to show some work, like where's dy dx coming from. So I'm just going to write, because I already have defined them in the previous part, y prime of 2 over x prime of 2, right? It's dy dt over dx dt at 2. And so here's a calculator screenshot of what I've done. And we can see from that we're going to say that theta is the inverse tangent of y prime of 2 over x prime of 2, which we got was approximately 0.081. That's in radians, but it doesn't matter because you should always be in radians. All right, let's take a look at part C of this thing. Find the distance traveled by the particle on 0 to 3. This is super straightforward. You were asked this question a ton. Like if you were dealing with parametrics, you're almost certainly at some point, on a free response question at least, you're going to be asked for distance traveled. So we know that that's going to be the integral of the magnitude of velocity or the integral of speed. Those are equivalent things. So we got integral from 0 to 3 of, and then it's the square root of x prime squared plus y prime squared, and then dt. So here's a calculator shot of how I did it. I always like to do these two different ways. Well, I like to do it only one way when I'm doing the problem, but I always think about it two ways. Either one you choose doesn't really matter. You will get the same answer. So we got approximately 4.669. All right, let's take a look at the last problem in this problem set. A little bit different. We're going to integrate 1 over the square root of 8 minus 2x minus x squared dx. So I look at that and I think like, if there were x's in the numerator, I'd be trying u substitution right away. There aren't, so I'm thinking immediately I probably need to complete the square. So to do that, I like to rewrite things. I hate negative leading coefficients, but also I can't factor when the x squared isn't first. Like if it's written from constant to linear to quadratic, I can't factor that way. So I've rearranged it. Negative x squared minus 2x plus 8. I'm going to take the negative out of just x squared minus 2x. So that's going to give me negative quantity x squared plus 2x. And then let's just leave the 8 over on the side, which is how I always do this. You take the coefficient of x, divide by 2, that's 1, square it, that's 1, add it and subtract it. So we have this. Now the first three things there are your perfect square. So we have negative quantity x plus 1 squared, and then we have to distribute the negative to negative 1, making it plus 1, and add that to 8, so we get plus 9. All right, so we can rewrite our integral, and we should. We're going to have the integral of 1 over the square root of 9 minus the quantity x plus 1 squared dx. You do u substitution on this, whatever you want. I'm looking at this and I think this is arcsine. And if it's arcsine, I really need that to be a 1, not a 9. So I'm going to factor 9 out of the radical. That's going to be the square root of 9, which is 3. So I'm really taking 1/3 out because it's in the denominator. So I have 1/3. And then this is left over, so it'll be 1 minus. Now what I've done is I have the quantity x plus 1 squared divided by 9, but those are both perfect squares, so I'm just going to make it x plus 1 over 3, the whole quantity squared. Save myself a little work. So we have this. Now you can do your u substitution with u is equal to x plus 1 over 3. There should be a 1/3 in the numerator, so a 3 on the outside. And then 3 and 1/3, those cancel out. Perfect integral, perfectly arcsine of u. So this will be arcsine of u in this case is x plus 1 over 3. And that's it. All right, that's the entire problem set. I hope this was helpful, and good luck.